Swayam Prabha. Digital India. Educated India.
We have been discussing flow through porous media, solved different examples and tried to convey this message that in what way the flow modeling can be done. We have also talked about the hydraulic conductivity, the coefficient of permeability, and I will discuss a bit more on coefficient of permeability in today's lecture. So, basically K depends upon several factors, and these factors are the porosity or void ratio, the particle size distribution, characteristics. We have used this concept of D10 and so on. The third parameter on which the K depends upon is the shape and orientation of the particles. The fourth parameter on which it depends upon is the saturation. And normally we define this as S. The another parameter on which it would depend is the type of cations, which are present in the soil mass, and the thickness of diffuse double layer. DDL stands for diffused double layer. We also call this as the adsorbed layer, and which is an indication of the activity of the minerals. So, if you remember the way we have defined K, we said K is equal to capital K multiplied by rho upon mu into G, and where capital K we have defined as the intrinsic permeability. So, basically K depends upon the density of the fluid and the viscosity of the fluid, and these two get influenced by the temperature. Alright. Now, this is a complete matrix. So, how the environmental conditions influence the hydraulic conductivity or coefficient of permeability, because they affect the density and viscosity of the fluid which is permeating, and these are the other parameters. So, the first parameter, if you want to understand what is the influence of the porosity or the void ratios, this is what is known as the Kozny-Karman relationship. This relationship is valid for mostly coarse grained materials. And it is written as the coefficient of permeability is equal to 1 upon C multiplied by T square into S square. C is the shape factor, it is understood that if the particles are spherical in nature, coefficient of permeability is going to be higher as compared to the particles which are flaky or the particles which are angular or subangular. T corresponds to the tortuosity. If you remember, we have talked about this in the previous lecture. Tortuosity factor is the length of the tortuous path divided by the L is the physical, or you may say this is tortuous path is nothing but the microscopic path or microscopic length, and this is the macroscopic length. Tortuous, tortuous. So, this is a square of T term and S corresponds to the specific surface. I hope now you can realize that it is not going to be easy to determine these coefficients, and this parameter, these parameters can be obtained with the help of advanced instrumentation. So, this is E cube over 1 plus E multiplied by the density of water upon viscosity of water. The best way to find out shape factor would be laser microscopy. You can define the term that how the shape looks like. Tortuosity factor is a very difficult parameter to determine unless you go for some advanced instrumentation scheme like CT scanning, alright, or 4D X-rays. These are the techniques which are being used nowadays. This equation is normally not utilized for fine grained soils. Alright. Basically what it indicates is that K is a function of E, and you will find different variants in the books where people have tried with E upon 1 plus E also, but this is quite prevalent and this is what is known as Kozny-Karman relationship. Shape and orientation of the soil particles. You remember we have talked about the shape already. So, granular materials which are spherical in nature. So, this is number 3, spherical grains show very high hydraulic conductivity for the same density, remember, as compared to the fine grained materials. Now, as far as the orientation of the particles is concerned, I hope you remember this equation or relationship which I had plotted some time back when we were talking about the compaction curve, and what I had shown is that if this happens to be the OMC, you have the variation like this. alright. So, this is how the variation of permeability or the coefficient of permeability would be with respect to moisture content. So, at OMC the K value is minimum, on dry of optimum the hydraulic conductivity increases a bit with increase in the moisture content, and the best way to learn this would be the compaction curve, if you remember. So, this is the moisture content and this is the gamma D. So, these two are in combination to each other. Another thing we should remember is that on I am sorry, it is not dry of optimum, this is wet of optimum. You should correct me, and this is dry of optimum, alright. So, dry of optimum we have particles which are highly disoriented, alright, we call them as flocculated. And on the wet of optimum we have the particles which are more dispersed. So, by definition or by fundamental nature, a dispersed structure shows less hydraulic conductivity as compared to the flocculated structure. Then we talk about the formation also. And when I say formation, this could be basically geological formation. There are two types of systems we come across. This is the layered soil mass, and once you say layer number 1, layer number 2, layer number 3, it so happens that this has become heterogeneous soil mass, clear. But the assumption here is that each layer is isotropic in nature. So, I will be discussing more about this isotropic nature or heterogeneity of the material. What isotropy indicates is, if I take a point and if I measure its properties in the x, y and z direction, all the properties are going to be same. This is the isotropy, fine. But because of the multi-layered system, it becomes inhomogeneous or heterogeneous. So, a heterogeneous system could be isotropic layer wise. So, isotropic nature means the properties are same at a given point in all the 3 dimensions, alright. Now, this type of formation may occur in nature by virtue of deposition. You remember we had talked about all these things quite earlier when we were talking about the how soils are formed. So, in this case we would be very eager to know what happens to the hydraulic conductivity when the flow is taking place perpendicular to the bedding direction. So, this is the flow which is perpendicular to the plane of bedding. What is bedding? Sediments are being carried by the rivers, and because of the density contrast or because of gravity they settle down. So, the formation of the entire soil mass is taking place layer wise. Horizontal lines which I have shown are the bedding planes, and this indicates the discharge in the vertical direction which is perpendicular to the plane of bedding. I will be more interested in also finding out what would be the QH. So, this is the horizontal flow of the fluid which is taking place through a layered system, alright. Now, I hope you can realize that this is going to be the parallel to the bedding. Now, as far as the saturation is concerned, there is a relationship between K and S. So, saturation of the soil is defined as, I hope you understand, the amount of water which is present in the pores to the volume of the pores. Okay. So, normally this is a cubic relationship. Those of you who might get a chance to work in all these petroleum companies, Schlumberger and what not, Shell, you will be using throughout your life this type of a relationship, because soils are not going to be saturated always. Why? Because you have a lot of methane, a lot of gases trapped in the sediments, clear. So, this is a relationship which you are going to use. Normally we define saturation as something which is greater than 90%. Alright. So, if soil sediments are approximately or greater than 95%, we call them as saturated. If not, they become unsaturated, and about 30% less than, we define them as dry. Alright. So, this is the relationship as far as saturation is concerned. Now, what is going to happen to the type of the cations? The more presence of active minerals, alright. So, if active minerals, their fraction increases, I have defined this as active minerals, alright. What is your guess? So, the more the active minerals present in the system, the double diffuse layer is going to be quite big, the resistance offered by this system to the fluid flow is going to be less, and hence your hydraulic conductivities are going to be less. The same thing is valid for the cation exchange capacity also, alright. Number 6, I think this we have already discussed. So, K would be proportional to density of the fluid, alright, and inversely proportional to the viscosity of the fluid. Is this okay? So, a denser fluid is going to permeate easily provided its viscosity is less. Is this part clear, or vice versa? Any questions? We have also talked about the methodologies for determination of K. So, until now we have discussed two methods which are mostly the laboratory methods. If you remember, these are the constant head test, and the falling head test. There is another test which we will be defining very shortly when we talk about the consolidation characteristics of soils. So, I can use a consolidometer to obtain the K value. This is to be discussed slightly later when we discuss about the consolidation characteristics. As I said, another method would be a triaxial method or triaxial tests. As far as the in situ tests are concerned, what we do is, number one, a pumping in test. So, we will discuss about this, or it could be a pumping out test. What we do is, we drill a well and then pump out water or pump in water, and we see how much the drop in the head is going to take place in unit time. There is another series of tests which is known as the Packer's test. Alright. There is another interesting way of defining the permeability of the formations under in situ conditions, particularly those of you who will get a chance to work in deep excavations in rock mass would be Lugion test. We call this as Lugion index. So, this is what is used for fractured rock mass. Incidentally, one of the ways to define the hydraulic conductivity would be in the units of Darcy also. So, K can also be defined in the form of Darcy, alright. Depends upon in which continent you are working and in what type of problems you are working. Any questions related to this? No? Alright. So, let me take up now some in situ tests. When we talk about the in situ test, we have to be very particular about in what type of aquifer I am working. This could be the confined aquifer. In your hydraulics course, I am sure you must have studied this. And the second one is the unconfined aquifer. So, by definition, suppose if this is the ground level and if I drill a well, this is a bore well. Sometimes people also term this as a tube well. It is basically a bore well. You are boring into the soil, cutting the soil and putting down a casing, and most of the time this casing is perforated, alright. So, this becomes a bore well. That means you have bored the soil and then you have lowered down the stainer or a casing which is made up of steel to support the soil, otherwise soil will collapse and the well is not going to function. So, this is perforated, and suppose we have a water layer somewhere here, initial water layer somewhere here. This is the water table, not water layer, sorry, water table, and somewhere here you have a hard rock. Alright. And this is the soil mass. The system in which the boundaries are not defined, clear, and they are open, this becomes unconfined aquifer. Okay. So, you have to monitor closely the difference between 2 and 1. When I draw the figure for 1, I am just discussing now the unconfined aquifer case. Now, suppose if I start pumping out water, what is going to happen? This water table is going to diminish, lower down, clear. We had talked about effective stress analysis when the groundwater table decreases. So, imagine there is a building somewhere over here, alright, and without telling you, someone starts a industry and he or she is trying to suck out all the water for creating, let us say, utility items. Now, what is going to happen? This water table is going to subside. Is this okay? Because of the discharge pumping out operations. This is the steady state situation. I would say a final state, because I have written steady state. Is this okay? Now, the way these tests are done is you create a well of certain dimension, start pumping out, and then you create 2 observation wells. So, observation wells could be located in the vicinity. This is observation well number 1, this is observation well number 2, and what we are going to observe? How much the groundwater has depleted. Is this okay? Delta H in both the cases. So, this is in ground, this is in the well number 1, observation well number 1, this is observation well number 2. I hope you can understand that this delta H is nothing but again the discharge which is taking place. No, sorry, this has been created because of discharge Q. Is this okay? Q has caused this delta H1 and delta H2 to appear. Now, suppose if I define the well radius as capital R, from the radial distance to this is, let us say, R1, this is R2, alright. And suppose if I take at a distance of R another hypothetical well which represents a hypothetical surface, okay. So, this is a hypothetical surface. I hope you can realize when you are pumping out water, the discharge is going to take place perpendicular to the surface. Is this correct? Have you understood this? So, this is a sort of a cylindrical curved surface, perpendicular to this the discharge is going to occur. So, if this is R and thickness of this element is dr, clear, height of this surface is, let us say, h, fine. Can I write a relationship between Q as a function of R1, R2, H1, H2 and so on, because Q is nothing but K into I into A. Is this okay? So, K is the principal unknown. Remember, we are doing the field test to obtain the coefficient of permeability. What is I? Area is not an issue, area I can obtain. What is the area? The curved surface will be 2 pi r into h. Is this okay? So, I need not to bother about this thing. So, that means area will be 2 pi r into h. What is I? Hydraulic gradient. Now, how would you find out a hydraulic gradient? Now, this is where we have to take help of a theory which is known as Dupitt's theory. This is valid only very close to the wells. So, as you go away from the well, what you will observe is Dupitt's theory is not valid because this curve flattens. Now, as per Dupitt's theory, the slope of this line corresponds to the I value. That means del H upon del R would be equal to I. Is this okay? Now, what we know? We know the value of Q because the moment I start pumping out test, I know how much volume of water I have taken out per unit time. So, Q is known. I have two observation wells. Why? Because if you substitute these values over here, you will realize that this is going to be a quadratic equation. So, K into del H upon del R multiplied by 2 pi R into H, okay. So, K I into A. So, I can write this as del R upon R equal to K by Q and 2 pi into H into del H. Is this okay? So, del R upon R equal to K by Q del H 2 pi H. Now, this becomes my governing equation. I can solve this easily. What I have to do? The whole idea of creating 2 observation wells was, I know the R1, I know the R2, clear? I know the total values of heads and I can solve this expression. Is this okay? So, what I can do? I can use a sort of a magnetic tape, not magnetic tape, I can use a device, electronic device, I will lower it down, the moment it gives me a beep, it is understood that I have touched the water table, I know this value, similarly I know this value, I can substitute over here and I can get the values of K. The difference between this situation, which is now, so basically what is the difference between unconfined and confined aquifers? The more you take out water, the more water table keeps on drowning, there is no constraint on this. So, these type of aquifers are known as unconfined aquifers. Now, suppose if I introduce a layer of aquifer in this manner, this is the ground surface and this is the layer of the aquifer. This is the hard rock, this is the ground surface and this happens to be, let us say, a clay of seam of clay, and I am pumping out water. I hope now you realize that this is what is going to be the soil mass, and what has happened? The soil mass is now constrained between the 2 impermeable boundaries 1 and 2, clear. So, what is going to happen? This surface is always going to be bound by this. Is this okay? So, that means when you have put a constraint on the porous media through which the discharge is going to take place, this becomes a confined aquifer case. Here what is happening? Here the surface area is changing with respect to time. The more you pump out, this value of H keeps on dropping down. Here this is going to be constant, and then what about the water table? The water table would be somewhere here. This is the initial water table, okay, and the more and more I suck it out, what is going to happen? It has to be below this, that is it. So, if you solve this expression, what is going to happen here? This your area term will be, if I take it as a distance of r, this will be 2 pi r into h, h remains constant. Now, we are going to use these concepts quite a lot in